Dear students, let's start e-lecture series on course Atomic and Molecular Spectroscopy. Course code, PHYS 4009. Today's lecture topic is X-ray spectroscopy. Here we start with the introduction of X-rays. X-rays were discovered by the German physicist W.C. Röntgen in 1895. Röntgen accidentally noticed that fluorescent materials showed a faint glow when placed near a cathode ray tube powered by a high-voltage induction coil. Since he was the first one who observed a new kind of rays, he called them X-rays, X equals unknown. Thereafter, he started systematic research on their properties. Now let's see how X-rays can be produced. Here you can see the picture of X-ray tube and in animation that, X-rays are produced by accelerating electrons with a high voltage and allowing them to collide with a metal target. Let's see some important properties of X-rays. X-rays are invisible electromagnetic radiation having wavelength ranging from 0.01 nanometers to 10 nanometers, which are shorter than those of ultraviolet rays, and typically longer than those of gamma rays. They are unaffected by electric and magnetic fields. Also, they are capable of ionizing gases. And they are also capable of inducing biological reactions. Now, how X-ray spectrum looks like. X-ray spectrum is represented by a graph showing the relative intensity of X-rays emitted by a source at different wavelengths. Here you can see that the continuous spectrum is overlapped by two sharp peaks. The two sharp peak corresponds to characteristic X-ray and the continuous variation of intensity corresponds to continuous X-ray. The two sharp peaks, they are characterized as K alpha and K beta. Characteristic X-rays are emitted when high-energy electron hits the target of heavy element. The bombarding electrons ejects electrons from the inner shells of the atoms of the metal target and creates a vacancy. These vacancies are quickly filled by electrons from higher energy levels, emitting X-rays, with sharply defined frequencies associated with the difference between the atomic energy levels of the target atoms. The characteristic X-ray emission are the two sharp peaks in the X-ray spectrum, as shown in the previous slide. Here you can see with animation the origin of characteristic X-ray. The high-energy bombarding electrons ejects electrons from the inner shells of the atoms of the metal target and creates a vacancy. These vacancies are quickly filled by electron from higher energy level by emitting X-rays, with sharply defined frequencies associated with the difference between the atomic energy levels of the target atoms. The energy absorbed by an atom transfers to the electrons of inner core shells of the atom, which are then ejected from the atom and vacancy is created. The atom is left in an excited state with an empty electronic level. The vacancies quickly gets filled by dropping down the electrons from higher energy levels, emitting the X-rays with sharply defined frequencies associated with the difference between the atomic energy levels of the target atoms. Any excess energy is given to the ejected photoelectron. The X-rays produced by transitions from L to K level are called K-alpha X-rays, and those starting from M to K level transition are called K-beta X-rays. Here we try to understand the origin of continuous X-rays with animation. When high-energy bombarded electron pass by the positively charged nucleus of the target atom, the path of the electron changes due to Coulombic interaction with the nucleus. The change in path causes acceleration, here it is deaccelerated. According to theory of electromagnetic radiation, accelerated charged particle emits radiation. It is called Bremsstrahlung. Bremsstrahlung is a German word, which means breaking radiation. It is emitted when electrons are decelerated or braked while passing by the positive charged nucleus of the atoms of the target. Accelerated charges give off electromagnetic radiation. And when the energy of the bombarding electrons is high enough, that radiation is in the X-ray region of the electromagnetic spectrum. It is characterized by a continuous distribution of radiation. It becomes more intense and shifts toward lower wavelength when the energy of the bombarding electrons is increased. If the graph of continuous X-ray radiation is studied with varying the energy of the bombarding electrons, it is observed that as the energy of the bombarding electrons are increased, the peak of continuous X-ray shifts towards the lower wavelength and the relative intensity go on increasing with energy of bombarded electrons. Absorption spectrum of X-ray. If the emitted X-ray radiation is being absorbed by the substances, we observe edges in the spectrum as the discontinuities in the continuous spectrum. And these edges are characterized as absorption edges of K shell, L shell, and M shells, etc. The spectrum shows sharp discontinuity in the absorption spectrum of a substance. These discontinuities occur at frequencies where the energy of an absorbed photon corresponds to an electronic transition or ionization potential. When the energy of the incident radiation becomes smaller than the work required to eject an electron from one or other energy states in the constituent absorbing atom, the incident radiation ceases to be absorbed by that state. For example, incident radiation on an atom of a frequency that has a corresponding energy just below the binding energy of the K shell electron in that atom cannot eject the K shell electron. Similarly, for the case of L and M shell electrons, we have observed that the X-ray spectra show set of discrete lines. They are designated as K series, L series, M series, etc. The first line of K series is K alpha. The wave number corresponding to the K alpha line for the atoms with different atomic numbers E can be expressed as. Similarly, the expression for the first line of L series, that is L alpha, is where R is Rydberg constant and sigma K and sigma L represent the screening constant for the lines for K series and L series, respectively. If we plot the square root nu versus z graph for different elements, we observe linear relationship. This is known as Moseley's law. Here you see the Moseley's diagram of X-ray spectra absorption edges as function of z for different elements. Screening doublet law. As we see that X-ray spectra has certain doublets for which the Moseley plots show parallel lines. These doublets are called screening doublets as it arise essentially due to the difference in screening. For pair of line the difference square root of nu upon r is a constant and essentially independent to z, which is the characteristic of screening doublet is known as screening doublet law. The two levels with same n and l but different directions of spin, that is, with different values of j are called spin doublet. The energy difference between two spin relativity doublet is proportional to the fourth power of z minus nu, where nu as a function of n and l is the internal screening constant which is appropriate for the spin-orbit interaction. This is called spin relativity doublet law. Auger effect. The Auger effect is a physical phenomenon or process by which electrons with characteristic energies are ejected from the outer energy level of the atoms in response to the filling of an inner shell vacancy of an atom by another electron in the atom. In this process, when an inner shell electron is removed from an atom, an electron from a higher energy level quickly make the transition downward to fill the vacancy. Sometimes this transition is accompanied by non-radiative energy. The energy released by the downward transition is given to one of the outer electrons instead of emitting a photon. And this electron is then ejected from the atom with an energy equal to the energy lost by the electron which made the downward transition minus the binding energy of the electron that is ejected from the atom. We can visualize the Auger process in this animation. Okay. What we learned from today's lecture. We learned what are X-rays and how they are produced. Properties of X-rays. Types of X-rays and its origin. X-ray absorption and its characteristic properties. Moseley's law. Screening effect on X-ray spectra. Auger effect and its origin. There are some books for further reading the topic in detail. Atomic and Molecular Spectra by Raj Kumar. X-ray Spectroscopy. An Introduction. By B. K. Agarwal.